I'd like you to consider this titration. This is more complicated, and I think it is quite important in terms of interpreting what goes on in a titration. Please take note that this is about a weak acid with a strong base. The weak acid in question is this guy right here. The strong base is our hydroxide ion once again. Write a balanced equation for this titration reaction. Please omit any spectator ions. So of course we do have sodium ion as a spectator ion, so we'll omit that. In this case, is it okay to say this is the hydronium ion? And the answer is no, it's a weak acid. The main species present is that, and this is methanoic acid or formic acid, right? So just to make the connection, it's the simplest of the carboxylic acids. Let me try drawing that again. It's the simplest of the carboxylic acids. So there's just a hydrogen attached here. It's just one carbon chain. Again, just to make this a little easier, I'm going to abbreviate him, not as a shooting arrow at the outside there, but as HA. So essentially all weak acids can be represented as HA. So write a balanced equation. This would be HA plus hydroxide ion concentration going to form. Now, I think what might be helpful is on the side, let's also write another reaction for HA, but with water. So I just want to contrast, because actually there are two things going on. There's HA and water, and then there's HA reacting with a hydroxide ion. So before we finish this, let's come up to there. What would be the products of HA reacting with water? Yeah, nice, okay. And note that I use the equilibrium arrow to say, remind us that this is a reversible reaction. And I think you probably remember, given a weak acid, that the equilibrium favors the reactants. There's very little A negative or hydronium ion essentially compared to the HA. What's different about this equation here? It's HA, strong base. It's really important to keep those two reactions separate. This reaction goes 100%. If it didn't, it would be almost impossible for us to do a titration. You wait till it arrives at equilibrium, and it's like, oh, we're only partway there. No, we need those to go to completion. So even though that's a weak acid, because that's a strong base, these reactions go to completion. The product, different products. What are the products this time? Yes, definitely uniform water and A minus. Of course, just for clarity, I like to keep things as simple as possible, but just to remember that, the HA is representing the formic acid and the A minus is representing the formate, the conjugate base. So those represent real things. I'm just trying to focus on what's really changing. If we contrast this to the strong acid, strong base titration, you may remember that this was water, and then we would have had sodium ions and chloride ions, but we would have omitted them. They're spectator ions. You can't omit this. This is not a spectator ion. So now when we label our graph, and so I'm thinking about, the questions are found on the next page. Key question 4, write a balanced equation for this reaction. Please omit any spectator ions. List on the pH graph the predominant species in the erlenmeyer before the titration, halfway through, and at the equivalence point. So to begin with, HA. Now, again, to find the equivalence point, it's this idea that you're looking for that drastic change in pH, and essentially you're trying to find that midway point between these two slopes, which I would estimate might be somewhere around where I made that dot there. So could you help me estimate what's the pH at the equivalence point? Approximately what? Again? Yeah, it sounds good. Okay, about there. Maybe we'll do it to 2 sig figs. Roughly, yeah. It's not 7. Why is it not 7? So HA is present at the beginning of the titration. What is the predominant species present at the equivalence point? Right? So at the equivalence point, you've added enough of this to completely use up this. So this is why I say it, saying that there's a strong base present and predominates is not the best answer, in the sense that what you have present at the equivalence point is this. Not just water and sodium ions and chloride ions, but A negative. What do you know about A negative? What's its job in life? Yeah, it's a weak base. So what do you know about HA? It's a weak acid. So hence, at the beginning of the titration, the pH is on the acid side. What do you know about the A negative? Well, it's the conjugate base of a weak acid. What's the job of a conjugate base of a weak acid? It's a weak base. Why is the pH at 25 degrees Celsius above 7? Well, it's because you got a weak base present. So assume we're, once again, working at 25 degrees Celsius. So if I have to list the predominant species, it's A negative, which is, of course, a weak base. Yes, I know there's some sodium ions present. I don't really care about the sodium ions. Oh, I just need to check something here. Okay, am I going to, hello, pen? Go previous. I might have previous. Whoa! So I'd like, if you wrote something that I wrote on here, I'd like you to erase it. In the sense that I was talking about what are the predominant species present. This at the beginning of the titration. Of course, it would be in here. Would we have any sodium ions yet? No. Who wrote that? Please, please get rid of those sodium ions. Right? Of course, it'd be just chloride ions. Now, of course, both of those would be present at the equivalence point. Good thing we caught that. HA, A negative. There's another point on this graph that we need to think about. So remember, we started with HA and then we end up with A negative. So effectively, the titration involves changing this into that. Of course, that doesn't just happen all at once. So as the titration proceeds, this concentration starts to decrease and this concentration starts to go up. So let's consider halfway through the titration. Halfway through the titration, in this particular titration, would be right here at 12.5 mils. What's present at 12.5 mils? Well, we've got both HA and A negative. What can you say about their relative concentrations? Exactly. Halfway through the titration, we've depleted the HA by half, and the A negative's concentration has gone up by the same amount. Just a few seconds ago, we saw that when the HA's concentration equals the A negative concentration, it's kind of a special moment in terms of any special moments in chemistry. I'm going to grab the Henderson-Hasselbalch equation again. pH is equal to pKa plus the log of the A negative concentration over the HA concentration. When these guys are equal, that ratio would equal 1. What's the log of 1? 0. So the pH would equal the pKa. I got to get, there we are. So, oh, come on. Go, 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 go. Aye. Yeah. Oh, this is interesting. I know I can do this. All right. So this is why that halfway point is actually quite important. We should be able to read that pH, and the pH will tell us the pKa. It's a way of finding out the equilibrium constant, not for a titration reaction, but for this reaction. Right? So I'm going to have all kinds of lines all over the place. The pKa that we're finding out is the pKa for that reaction. So from a titration, we find out about an equilibrium reaction. Well, for that whole reaction, right? That reaction has a Ka. How the Ka? Well, you can do some measurements, just weak acid and water, but you could also do this titration. From this titration, you can find out the pKa, which will allow you in turn to find out the Ka. So let's complete the last bit of calculations and things that you're asked to do here. So we wrote the balanced equation. The next thing is calculate the concentration of the formic acid. And once again, this calculation is going to be quite similar. I'm just going to write once again the balanced equation and remind you what you know about. So you've got H2O, we've got A negative. What do we know about each of these things? Well, we know the volume of the HA. We don't know its concentration, so the volume would equal 0.0200 liters. I'll change to liters already. We know the concentration of the hydroxide ion because it's 0.100 molar, and we know the volume required in the titration, which would be 0.0250 liters. So the same kind of calculation that we did just a minute ago. In fact, the numbers are identical. So when you go to do the calculation, it's going to look something like this. So there's the volume of the NaOH at the equivalence point. This is the ratio of the two chemicals in the balanced equation, and then the volume of your acid. The volume of your acid that you pipetted into your Erlenmeyer is what I wanted to say. Note this concentration. How does that concentration compare to the concentration of our strong acid that we looked at just a few minutes ago? Take a peek on the previous page. They're the same, yeah. So one of the things to keep in mind is if you have equal concentrations of a strong acid, weak acid, it will require the same amount of base to reach the equivalence point. The next question here, which is number 7, the pH after the addition of 12.5 mils, so we're halfway through the titration, is 3.745. I expressed it to 3 sig figs. Use this information to determine the pKa and the Ka for the formic acid. This is similar to something that you're going to need to do in the lab, because you're going to need to find out, well, what is half volume of the equivalence point? What is the pH at that volume? And of course, that pH will equal to pKa. So the calculation would look something like this. So the pKa is equal to 3.745. So it's just grabbing that number. The Ka is equal to 10 to the negative 3.745. Can someone help me with that calculation, please? To 3 sig figs, 1.79 times, yeah. So there's our Ka. Again, something similar that you'll need to do in the lab.